Atomic size. We're beginning here to look at some periodic trends. Atomic size is one of them. There are different ways to define the size of an atom. It's a little different than just measuring the diameter of a bowling ball or something, because they're not solid. They've got this electron density cloud thing going on, and how do you decide what's the edge of the electron cloud? It's very fuzzy, literally. So there's a couple of different ways. You can use the non-bonding atomic radius or the van der Waals radius. And here we're looking at half of the distance between adjacent nuclei in the atomic solid. So here is krypton cooled down to be a solid. The krypton atoms are not bonded to each other. They're just frozen. And so they're stuck here, and we can detect the nuclei, and so we can actually measure the distance between the two nuclei. And so one way to define the size of an atom is say, well, the radius must be half that distance between the two nuclei. We can also look at a bonding atomic radius, or it's sometimes called a covalent radius. For nonmetals, we're looking at half the distance between two of the atoms bonded together. So bromine forms diatomic molecules. We can measure the distance between the bromine atoms in the molecule and divide that by 2. Now, as you can imagine, that's going to be a little smaller than if you had a bromine atom all by itself, because they get pulled together and they squish into each other. For metals, we're looking at the distance between two atoms in a crystal of the metal. And so for metals, half the distance between those two is going to be real similar to the non-bonding atomic radius. So what we're going to use is the term atomic radius, just an average atomic radius based on measuring large numbers of elements and compounds, just kind of a general term. And when we talk about bond lengths for covalent bonds, we can approximate them by just adding the atomic radii of the bonded atoms. So just, kind of as an example here. So if this radius was, say, 1, we'll call it 1, that's a distance of 1 Kawagoe. And this is a distance of 2 Kawagoes. I just made up a new unit. Then we could say, well, that bond length then must be 3 Kawagoes long, right? And we sometimes do that for covalent bonds. So you kind of got a preview of this by trying to work on that worksheet and try to figure out these things that I hadn't really talked to you about. There's a term for that sort of learning, and I just forgot the name of it. Frustrating. Yeah, there's a term for it. It'll come to me later when it doesn't matter. Anyway, if we look at trends in the atomic radius, we can graph atomic radius here in picometers, really small, versus atomic number. And we don't see a nice linear graph here by any means, but we see some trends. It goes up and it comes down. It goes up and comes down. And the ones here at the peak, these are the alkali metals, the metals in group 1A. And there is a trend here. It's not linear, but as you go further down the periodic table, the atomic radius increases, the atoms get larger. And that makes a lot of sense, because cesium, how many electrons and protons? 55. Versus lithium has 3. It seems reasonable that 55 protons and 55 electrons is going to take up more space than 3, right? So that one makes sense. We can explain this using quantum mechanics by observing that the n, principal quantum number, is increasing. And we said that the principal quantum number gives us a size of the orbitals. As the principal quantum number increases, the size of the orbitals increases. I can't remember what comes next. Oh, yes, this one. So that makes sense. As we're going down a group, atomic radius increases. They're showing you the atomic radius as a number underneath here, but they're also representing it as the height of these little blocks. So we can see over here in the noble gases, atomic radius increases as we go down. But what doesn't immediately make sense is if we go from left to right across the period, the atomic radius gets smaller. It's like neon has more protons and protons and electrons than lithium does. Why is it smaller? What principal quantum number is filling up as we're going across period 2? Period 2 is principal quantum number 2, right? So neon's valence electrons, the outer electrons, are in period group. I might as well just throw the names of all my children in there too. Lately I've been calling everyone Michael. I'm glad I don't have a Michael in this class. That would be really confusing. Neon's valence electrons are in principal energy level 2, and so are lithium's valence electrons. So if it's in principal energy level 2, their valence electrons are roughly the same distance from the nucleus. So that explains why we don't see an increase in size as we go across, but why does it decrease? Well, that has to do with that idea of shielding an effective nuclear charge. So when we have a multi-electron system, there are electrons that are being attracted to the nucleus and being repelled by each other, because like charges repel each other. The outer electrons are effectively shielded from the nucleus by the core electrons. And that causes the outer electrons to not experience the full effect of the nuclear charge. So here's an example. This is lithium. Here's 3+. There's 3 protons in the nucleus, and lithium has 2 core electrons in the 1s subshell, and it has 1 valence electron in the 2s subshell. This electron gets shielded by these 2. The way I think of it is it's looking through here, and these guys are getting in the way. And so they are canceling out 2 of the positive charges here. So when this guy looks at the nucleus, he's seeing 1 proton. So we say the effective nuclear charge is +1, because these core electrons are between the valence electrons and the nucleus. Does that make any sense? It made sense to at least a couple people, so we'll go on. So effective nuclear charge is the net charge experienced by an electron. So if you want to be more mathematical about it, you say the effective nuclear charge is the actual nuclear charge, the atomic number, the number of protons, minus S, where S is the charge that's shielded by the core electrons. So S basically is the number of core electrons. Number of core electrons. Valence electrons make a very, very small contribution to shielding. So then the example asks, what are the effective nuclear charges of nitrogen and argon? Well, how many protons does nitrogen have? 7 protons. So it's got 7 protons, and if we look at the electron configuration, it's 1s2, 2s2, 2p3, right? So these are the valence electrons, and these are the core electrons, so Ce and Ve. Valence electrons and core electrons. So to calculate effective nuclear charge for nitrogen, we're going to take the actual nuclear charge of 7, and we're going to subtract 2, and we're going to get a charge of 5. So its charge is 5+. That's what these valence electrons out here see. Now what about argon? How many electrons does argon have? 18. So argon, it's got 18 electrons, it's got 18 protons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. How many core electrons does it have? It's got 10, right? There's 10 and 8 valence. So the effective nuclear charge for argon is going to be 18 minus 10, which equals 8. Which is bigger, 8 or 5? 8. The noble gases have higher effective nuclear charge because as we add electrons going across the periodic table, we're also adding a proton, but the electrons that we're adding are the valence electrons, and so they are not shielding any of the other valence electrons. And they're being added at roughly the same distance, but the effective nuclear charge is increasing. Higher charge, Coulomb's law says, is going to attract things more strongly, and so it actually just shrinks it in as it goes across. So as you go across a period, the atomic radius decreases. It's counterintuitive, but if you think about effective nuclear charge, it is possible to remember it. So moving down a column, the principal quantum number is increasing. That results in larger orbitals and larger atomic radii. As we go across a period, the effective nuclear charge increases while n is the same. And that results in stronger attractions between the valence electrons in the nucleus, stronger attraction pulling them in smaller atomic radii. Then there's those transition elements. In the same group, even in the transition elements, we do see an increase in size as you go down a column, just like the main group elements. But when we go across, the atomic radii don't change very much. And that's because they have the same number of valence electrons. And the d electrons are not valence electrons. They are core electrons. And so as you're going across the d block, you're adding a core electron and you're adding a proton, and so the effective nuclear charge is approximately the same as you go across. So let's go back to that graph. This one. So lithium is a main group, and beryllium's a main group. And then these guys here, these are the transition elements. Oh, I'm sorry, those aren't. There's no transition elements in that period. I have to go down to period 4, sorry. Yeah, look, it's even labeled there, duh. Okay, these are the period 4 transition elements. And there's a little bit of a trend here, but see how they're pretty much the same size? Because we're not getting a lot of change. Once we get out of the transition elements, these are main group elements, it's not a huge difference because it's just the effective nuclear charge messing with it, but they are just getting smaller and smaller, just a little bit. So what do we need to do? What should you know how to do? You should be able to do things like this. On the basis of periodic trends, choose the larger atom in each pair if possible. So tin or iodine. Which one is larger? So tin and iodine are in the same period. So the larger one will be the one to the left. So that'll be tin. It's really hard to do this on the screen without a periodic table. Germanium or polonium? Well, let's just draw a little piece of periodic table. Like that, a little piece of periodic table. Here's, we'll put germanium here, and then just relatively polonium's down here. So if we're going across, polonium falls to the right, and that would predict that polonium would be smaller. right? If we're not considering vertical, we're just looking horizontal. If we're doing the vertical, polonium is predicted to be larger or smaller than germanium. As you go down, it gets larger. So there are conflicting trends here. Do you remember that graph? Actually, I can go back there just one time. So this is the effect of going across a period, and this is the effect of going down a group. Usually going down a group is a bigger change than going across a period. So you could kind of, if you were forced, I would choose the vertical direction on that guy. If I was forced to make a choice, like you sometimes are on a multiple choice or a Mastering Chemistry, if I was forced, I would say that polonium is larger. But if I wasn't forced, I would say can't tell. Because this question does say, if possible. We have opposing trends. One trend says it's higher, one says it's lower. So it's iffy at best. How about chromium or tungsten? So here's chromium and here's tungsten. Tungsten's going to be bigger because as you go down, things definitely get larger. So W. Any questions? We're going to talk about several other trends, and it can be a little confusing because you have to remember across and down. And is it up, increasing or decreasing? And some people are good at just memorizing somewhat unrelated things. I'm not one of those people. The way I remember it is I think about it. So I think, oh, well, as we're going down, we're higher and higher principal energy shells. This is going to be getting bigger, and as we're going across, effective nuclear charge, blah, 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 and they get smaller. But you have to figure out what works for you. No.